Alright, so that should work. Alright, so yeah, I am doing my work at Hootsuite as lead engineer on the platform team, and so I just wanted to talk a bit about our scaling story. So if you don't know about Hootsuite, we're a social media management tool. Been around for about 6 years now. When I started about 5 years ago, there were 5 people and we had maybe 100,000 users. Nowadays we have over 800 employees and something over 10 million users. So we've been doing this so far all with PHP, and have of course faced quite a few challenges along the way. And so I wanted to sort of highlight some of the things that we've run up against and how we solve these issues. So this is a selected architecture. These are some of the things that I'm going to be talking about. And this is how they're all sort of laid out in the system. So users hit a pool of Nginx load balancers, which are backed by a pool of Nginx web servers running PHP FPM. These communicate internally with VMware boxes for distributed tasks, memcache boxes for caching, MySQL, which is our main database, and Mongo. And then they also communicate with a lot of internal services, which we're making a big push toward a service-oriented architecture. And so I'll talk about that a little bit as well. So when we started, it was Apache, PHP, MySQL, LangStack, very, very common. Then we ran into a problem. It's hard to scale MySQL horizontally, right? You need to deal with replication and all sorts of headaches. And so we decided that instead of dealing with scaling MySQL itself, we would add caching. So, oh yeah. No, okay, there we go. All right, so we implemented, we started using memcache. So memcache is a distributed caching system. It's basically just a bunch of boxes with a ton of RAM. You spin new ones up, it adds more memory to the cluster, and it's just a huge distributed key value store. So our philosophy with this was just cache everything, everything you can as much as possible, and invalidate it only when necessary. So we really try to use cache instead of the database wherever possible, and just be really aggressive with that. We also try to keep the joins to a minimum. So it's a little bit strange, but we try to not rely on the database as much as possible. And so instead of doing that, we try to decouple everything and do what we call collection caching, which I'll talk about in a minute. Also, we started using 2M proxy recently, which is a great piece of technology made by Twitter, who are also heavy users of memcache. And it's just a memcache collection pool, so you can install that on your web servers, and instead of having one persistent connection to your memcache servers for PHP thread or Apache thread or FPM worker, you just have one per box, and that will really help you scale out your use of memcache, because we were running up against limits of open connections at all times to memcache. So this is one of my favorite quotes. There are only 2 hard things in computer science: cache and validation and naming things. There's another version that's there are only 2 hard things in computer science: cache and validation, naming things, and off-by-one errors. But I feel like at Hootsuite we've been doing a really good job at cache and validation, which is a surprisingly hard problem. So this is an actual example from our code. This is the social network model, which extends the MySQL model, which extends the base model, which you'd assume is the lowest thing in the stack. But even below the base model is the base caching model. So this means that every model within the system is cached by default. So it's baked into everything. It's super easy for people to use. Every new model that they add, they don't need to worry about caching because it's just done automatically behind the scenes. So we found that to be really important. And then there are also a lot of options so that you can customize the behavior of it when you have a use case that's different. So the other thing that we do is multi-get and collection caching. So here's an example of where you're, say you're finding all the members who are in an organization. So we run this query if it's not in the cache. We get the data back from MySQL, and then we take the individual member data and put those into Memcache sort of one by one. So now we have member ID 1 as a key with member data as value, etc. And then separate from that, we also store a collection cache. So we take just the IDs that belong to this set of members within the organization 888 and cache just the IDs. And then on top of that, we have automatic collection caching, so that whenever a user is added to that organization, that collection is invalidated. But it invalidates only what it needs. So the collection is invalidated, which is only a list of IDs, so it's easy to reload that. And whenever a member updates their data, it updates only the member record, not any of the other member records, not the collection. So it's a very small sort of subset. I'll get some questions after. And then once we get these IDs out, we are using Memcache multi-get to load all of the contents of the member records. So I mean, it can seem a little counterintuitive as we often learn to lean really heavily on databases, but as you start to scale, that can be quite problematic. And we found it easier to scale with Memcache instead. So the problem was it's hard to scale MySQL horizontally, and now we have no need to scale MySQL at all. We run the entire site off of a single MySQL server, and where MySQL serves 500 SQL selects per second, say, Memcache will do 50,000 gets per second. So it's really, really heavily cached, and it has about a 99% plus hit rate. So we really heavily rely on that, and if that goes down, that's a huge problem. So the next problem we faced, we need a way to perform asynchronous tasks using a single-threaded language. Of course, there's pthread before, but PHP is not really multi-threaded. For example, here might be something like PDF generation, where you want to split off a task that's really CPU intensive, and have that be scalable independently from your web servers, which you don't want to have performing really CPU intensive tasks at the same time they're doing everything else they're supposed to do. Our solution for this was a software called Gearman. You basically distribute work out to other servers to handle. Workers are just using the same code base. It's a bit of a precursor to having a service-oriented architecture where you're truly distributing everything. And these days there are a lot of other solutions for this, queuing systems and stuff like that, but in those early days we settled on Gearman. This is sort of how it's set up. So you have clients which are running the PHP code. They send jobs to the Gearman D servers. These have a pool of workers behind them, and then basically just queues in front of them. So it accepts connections, and passes them off onto these PHP Gearman workers who just make themselves available for jobs. They process them, send them back. This can be done synchronously or asynchronously, and we've found that really to be valuable scaling. So we needed a way to perform asynchronous operations and distributed tasks. We moved a lot of that stuff to Gearman. We were able to scale the operations of those things separately from the web servers, which is really valuable when you need to think about how a certain system performs, right? You want to be able to tune the performance to the specific task that it has to do. And we're able to split things into discrete tasks and call them asynchronously in parallel. So the next problem was we need to store social network message data. So this was, whenever people send out messages within the system, which happens very, very often, we want to store that data and be able to do analytics on it and various things. So this definitely has the potential for growing too big for just storing in MySQL, and we didn't have a huge need for it to be relational data. So our solution for this at the time was MongoDB, which, it's working. There are a lot of other solutions these days. There are document stores like Couch and Elasticsearch, and key value stores like Redis and React and Dynamo. We found that a NoSQL database really did help here because, like I said, the data didn't need to be relational, and it let us just stuff tons and tons of data in there and still be able to get it back, reasonably quickly. We found it to be a bit of a pain. There are a lot of moving parts and trying to scale that up with many clusters with many shards. It can be tough. We also had to make our own sequencer to take advantage of auto-implemented IDs, which was a bit of a pain. But at the same time, it let us scale. So we had a problem with storing data like this. Now we have multiple clusters containing huge amounts of data, millions of rows per collection, and many terabytes of data on disk. And that really would have, been a huge problem if we would try to do that in MySQL. So at this point in the story, we have Apache, PHP, MySQL, Memcache, Gearman, MongoDB, growing list of technologies. Then, with a code base and an engineering team that's rapidly increasing in size, how do we keep up the pace? We were using Subversion at this point. We had these big long branches, and then basically I was in merge hell because I had to merge all this stuff together, and it was just horrible, and things were catching on fire, and it was the Wild West, which is fun, but it's not sustainable. So our solution for this, I know you expected me to say it, but it's dark launching. So this is something that we found to be incredibly useful. Some people call it feature flagging, but we basically wrap chunks of code in named blocks, and then we're able to access those on a management panel. So we can see a list of all of the features in the system at any given time, and be able to control the visibility of those to any user. So we can go in there and change it, just turn it on for everyone, or for no one. We can turn it on for a specific user, a specific organization, or say 15% of all users and stuff like that. So it really gives us a ton of control over the system. This is an example of what that looks like. Really simple, basically just a block checking if, say, Twitter ads is enabled. If it is, run the new code, otherwise run the old code. So the implementation, when it comes to the code that you're writing, is fairly simple. So it gives us a ton of control over the code. It really limits the risk, right? If you push something out and it's not working the way you expect, you can just turn it back off again. That means it raises the confidence in people who are pushing code out because they're not as worried about pushing code and then breaking production and then just being on the hook and things are catching on fire again. Which in turn speeds up the pace of releases. So people are able to push more often and have a lot more confidence in the code that's going out. We call this branching in production because basically now we work not on branches at all pretty much. We have tiny little feature branches that get merged after a couple of days. We try to keep everyone in master at all times, deal with integration issues really quickly, and push out code that may not even necessarily be ready yet, because if it's wrapped in a dark launch block, it's not visible to anyone. So the branching really happens in production. But we like to say that learning happens in production too. Like when you have code on production, that's when you know that it's working the way you expect. And so being able to push code out onto production, turn it on for yourself, and test it out on the real servers and test it out with real traffic is just an incredible thing. So I mean, I think it's one of the best decisions we've made, and has helped us incredibly. So scaling of our team. Pardon? Lost my screen. So yeah, with the code base and team increasing in size, how do we keep control of all this junk? So now we work a lot faster, we have a lot more confidence, we have a ton of control over our system, and we do usually 10 or 15 releases to production per day. Recently we switched to doing a push-based distribution of these dark launch codes with a system called Console. I just wrote a blog post about it, and you can check it out on our code blog at code.hootsuite.com. It's a very, very cool technology by HashiCorp. Problem after that, so rapidly increasing code base and amount of traffic, how do we keep visibility into the performance? Our solution for that was monitor. So stats via graphic for metrics. Logstash, Elasticsearch, and Kibana for log events, and then Sensu for monitoring. So I'll just go through these ones quickly. So this is a use of statsd. So this is an example from our code base, a timing call. We basically give it a identifier for the type of stat that we're tracking, which is just a little namespace identifier. And then for a timing call, we give it the amount of time that this thing took. So basically now minus the start time. And this is the kind of graph that we get out of this. This is another real example for the system. This is the amount of time that Facebook Graph API calls take. And so it gives us a ton of visibility into how the system is performing. And we just have dashboards and dashboards of this stuff, and people can customize those to the stats that they care about and add new stats that they want to get some insight into. For logging, this is logging using Logstash. So we have a log class, give it a message category, some metadata. And then we use a system called Kibana, which is on top of Elasticsearch and lets us look at this data. So we can see a graph of those events over time, and then also individual log entries and a lot of metadata about those. So we can see like the user that event happened for, and the web server it happened on, and the that person's IP and stuff like that. So it gives us a lot of visibility into what's happening right now in the system. So it's very important to have visibility of this stuff so that you can iterate on your code and actually measure the result of the changes that you're making, which is super important, because otherwise, who knows if what you did actually did what you think it did. It also pairs really well with dark launching. We can twiddle a knob and just see right away the graphs go up or down, and see if we broke something, and if we did, we can just turn it back off again. There are also systems like New Relic and AppDynamics that do this just sort of out of the box, but you can also, there are tons of systems for doing this on your own if you don't want to shell out for something like that. So with rapidly increasing code base, what do we do? Now we can watch the performance and the behavior in real time. We can see important events in the granular or the aggregate. And we can control the system and then immediately see the effect of our changes. So a few sort of optimization things that I want to mention that we ran into along the way. In general, things expand beyond their initial scope. One of the things that we ran into was with our translation system. So we have a crowdsourced translation project. And when this was first implemented, everything was good. We were chugging along. A year down the road, the site was just performing really, really badly, and nobody really knew why. It's not something that had happened overnight. It's not like our graph suddenly jumped up and there was a commit and we knew that there was something we could roll back. It just sort of got worse and worse over time until it was looking sort of like this. So this is the most deviant web level graph. So this is the worst performing web service in the cluster. And you can see there are about 10 of them that they all have a load of like 46, which is not the kind of thing you want to see. So after looking into this, we realized that when it was first implemented, the person who was doing it just didn't think about how this was going to grow over time. And so they were loading all of the translation strings for all languages, regardless of what the user had chosen for their current language. And as soon as we went in and made that change, it started looking like this. So if you're able to trim off 50 or 60% of our web load and our web cluster. So think about how your system is going to evolve over time and try to sort of future-proof yourself against that. Also, try to push work up to users within reason. Use your users' browsers. We were rendering streams in PHP, which was using the web servers to do a job that they didn't necessarily have to do, and so we just converted that to pushing JSON up to the users' browsers and have the browsers rendering it, and that can help shed a lot of the load. You just have to find a balance. You don't want to end up pushing so much up that your user experience is getting sluggish and nasty. Performance to us, we consider it to be more important than clean code or business requirements, where those things are mutually exclusive, which is not necessarily always the case. But really, we have to think about that if we want to be able to scale. There's also, a fine line between future-proofing and premature optimization. You want to be able to choose the big wins and think about your project size and do what's right for you. Also, make it easy for your team to do things the right way. Like with our VanPHP system, make it really easy for people who are writing code in your system to just do things the way you want them to do it, right? So give them the tools to make the right decisions. And also know where the weak spots are in your own code base so you can protect against them being abused by people who are writing code for you. Here's another example from our system. This is our dashboard controller. So this is, for every single line, there is